just say a few words. So welcome to the seminar today. So today as our speaker, we have Naomi Gendler, and she's now at Harvard. And she did her PhD with Liam McAllister, and now she's at Harvard. And today she is going to talk about something that we are interested to hear about, the connection between modular space reconstruction and weak gravity. So over to you, Naomi.
Okay, well, thank you very much. Thanks for inviting me to speak. Yeah, so today I'll be talking about this work that came out at the end of last year with my collaborators, Ben Heidenreich, Liam McAllister, Jakob Moritz, and Tom Rudelius. And just to give you the upshot of where we're going in this talk, what we'll do is we'll verify the lattice, actually, weak gravity conjecture in a large ensemble of M-theory compactifications on Calabi-Yau threefolds. And along the way, motivated by testing this conjecture, we'll learn how to compute the full Kähler moduli spaces of Calabi-Yau threefolds using BPS indices known as Gopa-Marvaffa invariants as input. Okay, so just to set the stage and sort of motivate where we're going, let's discuss the weak gravity conjecture in the presence of multiple gauge fields. So consider a gravitational theory containing some number n of some U1 gauge fields. Then specifically, so there's a lot of versions of the weak gravity conjecture, but the one that we'll be focused on today in this talk is the lattice weak gravity conjecture, which says that for each charge q in the lattice, there should exist a one particle state of mass m such that the charge to mass ratio of that state is bigger than or equal to the charge to mass ratio of an extremal black hole with that same charge. And so our goal is going to be to test this conjecture as best we can in Calabi-Yau compactification.
Can you explain what the numerator is? I'm sorry.
The numerator in this inequality?
It's a subscript G, yeah.
Yeah, so right. So this numerator just means the norm of so you take some charge in the lattice and you compute its norm using the gauge coupling G. So this subscript G is just to indicate that this is not the Euclidean norm, it's the norm using the gauge kinetic matrix.
Thank you.
And I should also say that the lattice weak gravity conjecture is known to be false in some contexts. So this is not, I'm not, it's actually a surprise here that it's satisfied in this setting. So I just want to make that clear. All right, so let's test the lattice weak gravity conjecture. How do we do this? Well, conceptually, it's straightforward, right? All we need to do is compute the spectrum of one particle states, which in this context are M2 branes wrapped on 2 cycles. But doing this is actually hard, right? We can't actually compute this spectrum in general. Something that's easier is to compute just the BPS one particle spectrum. So that's what we'll be focused on. But actually computing precisely the BPS spectrum is still too hard. So instead, what we'll do is compute some indices that reflect the spectrum, but don't capture it exactly. So let's see what I mean. BPS particles, as I said in this context, come from M2 branes wrapped on holomorphic curves, complex curves. So the relevant BPS indices are the Gopa-Marvaffa invariants. And these Gopa-Marvaffa invariants, which I'll label by a number n with a subscript q that indicates which site in the lattice we're looking at. And this 0 just means that it's the genus 0 GV invariant. This is given as a difference of the number of hypers minus the number of vectors plus some higher spin corrections. And these Gopa-Marvaffa invariants can be efficiently computed using mirror symmetry. This talk is not about computing these invariants. For the purposes of this talk, we'll just assume that these GV invariants are sort of handed down to us and we can just use them. But I refer you to these works for algorithms on how to compute Gopa-Marvaffa invariants using mirror symmetry. Okay, so at this point, it should be said that finding non-zero GV invariance, so finding n not equal to 0 for all charges Q in the BPS cone, would confirm the lattice weak gravity conjecture within the BPS cone. Okay, so let's now take a look at an example and see whether this is true in an explicit example. So as an example, we'll take a Calabi-Yau threefold that has H11 equals 2, and we can compute the charge lattice is two-dimensional in this case because H11 equals 2, and we can compute these GV invariants at every site in the charge lattice. And the surprising, well, maybe surprising thing that we see is that there's actually an infinite number of sites with zero GV invariance inside this cone, right? So there's this ray and this ray, and as we moved farther out in the lattice, we would see more and more zeros.
But this is an index, so it being 0 doesn't mean 0, right?
Absolutely, it doesn't necessarily mean 0. It doesn't necessarily mean that there are no states, no BPS states at that site. But even so, we'll take this example as motivation to see that or to explain why the weak gravity conjecture doesn't actually predict that every single site in the BPS cone has a non-zero GV or has a BPS state there. But yeah, that's true.
And what is the argument which says, which actually motivates that statement? Actually, I don't even get that.
Which statement?
That inside the cone that the numbers have to be non-zero. How that is.
That's not the correct statement. It's just that if it were true, it's a one way. Yeah, exactly. So if it were true that every site in the cone had a non-zero GV invariant, then we would be certain that there was a BPS state at each site, and we would have confirmed the lattice weak gravity conjecture. But I'm just using this example to motivate that it's not if and only if.
Okay, please continue.
What is this axis here in this figure? Two axes.
Yes. So these are just, this is just the charge
lattice.
lattice of H2 of X. Yeah.
Yeah. Thanks.
All right, so then, okay, let's be precise now. What does the weak gravity conjecture predict about BPS states? Well, for general charge, the weak gravity conjecture does not actually constrain the BPS spectrum. But for all charges such that at least spherically symmetric BPS black holes of that charge exist, then the particles predicted by the weak gravity conjecture have to be BPS. Okay, so the way we see this is that if we, the statement of the weak gravity conjecture is that the charge to mass ratio of a state with some charge Q has to be bigger than the charge to mass ratio of an extremal black hole with that charge. But if this is a BPS black hole that exists here, then the mass of that black hole just takes this form determined by the central charge, which in turn, this charge to mass ratio has to be smaller than the BPS bound. So what we find is that if there exists a BPS black hole with a certain charge in the charge lattice, then the weak gravity satisfying particle has to also be BPS. And so what we find is that the weak gravity conjecture predicts infinite towers of BPS particles in the cone of spherically symmetric BPS black holes, which I'll call CBH for the rest of this talk. Okay, so it's not actually predicting towers of BPS particles in the entire BPS cone, but just in this subcone where BPS black holes can exist. And this is the prediction that we'll test. Okay, so of course, now we need to know, where do these spherically symmetric BPS black holes exist? And so this is our first task, to actually compute CBH, which is this cone in charge space where extremal BPS black holes exist. And the fact that we'll use in order to find this cone CBH is the fact that BPS black holes exhibit a phenomenon called the attractor mechanism, where massless scalars flow to the same values on the horizon, regardless of their values at spatial infinity. So this is my little cartoon of the attractor mechanism. It's always a hit or miss with this cartoon, but basically what I want to show here is that no matter what color you start with at infinity, the colors always flow to purple on the horizon. So if that picture helps, that's great. And if it doesn't, just ignore it.
So a quick question about multi-centered black holes. Why should we disregard them?
Sorry, I'm not sure I understand the question.
So, I mean, the attractor mechanism is only for single-centered black holes, spherical symmetry, etc., etc.
Yeah.
Okay. So the question is, I mean, multi-centered obviously will only have axial symmetries. If you have two centers, it's worse than that. And so, question is, why do we not consider?
No, okay, I understand the question now. That's a great question.
Okay.
We totally should. But this is sort of like, this is the understanding where the spherically symmetric BPS black holes exist is sort of the most straightforward thing to get our hands on. And at least for non-spherically symmetric black holes, it's not even, I think, totally clear exactly what the weak gravity conjecture should say about them. But as you'll see later on, well, okay, maybe let's come back to this question later on, because there's maybe a hint that there's something to do with non-spherically symmetric black holes that's happening later on. But for now, we're just focusing on the spherically symmetric ones, not for a particularly principled reason, just because these are the ones where we know how to compute whether they exist or not. All right, so the upshot is that we're going to use the attractor mechanism as a diagnostic to detect BPS black holes within our charge space. Okay, so again, we want to compute this cone CBH to our best ability. And because of the attractor mechanism, there's a correspondence between the charges of spherically symmetric BPS black holes and the moduli vacuum expectation values on their horizons. And so
very naive question. I mean, is the attractor mechanism supposed to be generally true, or is it known only in certain examples, or why we believe it to be generally true?
Yeah, so it's generally true for BPS black holes. So these are yeah,
hence entropy function formalism that if you want to extremize the ADS2, if there is some entropy function, then automatically fixes the values at the scalars at the horizon. Is that
but it's single-centered spherically symmetric. You need, I mean, you can use any method to compute it. Entropy function is one way, but
yeah, but okay. And what I mean to say is that usually this happens if there is some C function or something, because it seems to be like a very, I mean, but is there some reason to believe there should be always such a function?
What do you mean by always?
I mean, like, the statement that you made is that you're using the attractor mechanism as a diagnostic to see whether such black holes exist. But then you're assuming that this is a very general, the attractor mechanism should generally hold for any
half BPS black holes in n equal to 2 supergravity.
Yeah. I mean, okay. Of course, here you are focusing on BPS, but I'm saying, is there a general? That my general question is that
no.
Is there a reason to believe that the attractor mechanism should always be valid for any extremal black hole?
No. It definitely is true that you can have extremal black holes that have an attractor mechanism that are not supersymmetric at all. But I don't think it's guaranteed for you.
Yeah, there is no, so we are just simply using it as just from experience, we know that this happens. So you're believing that.
In this talk, I'm specifically going to be concentrating on checking the weak gravity conjecture within the BPS sector. So all I care about are BPS black holes. and one of the reasons that's where we can compute things is because that's where we are guaranteed that the black holes have an attractor mechanism, so we can use that. So I'm never going to be in this talk, at least, talking about black holes that are not BPS, and we want to determine, you know, whether like what the extremality bounds are for those.
Yeah, I understand that, but even for BPS sector, is there some argument that there should be an attractor mechanism always?
Oh, yeah. I mean, for BPS black holes, for spherically symmetric BPS black holes, I think you are guaranteed to have an attractor mechanism.
I mean, is it the argument comes from something like the entropy function will always determine the values of the scalars, or there should be some other?
That I don't know. I mean, I think the simplest way to see it is that if you write down, like basically the Einstein field equations for one of these BPS black holes, what you find is that you can rewrite that set of equations into basically one equation, like that all the dynamics are determined by one function, which is called the black hole potential. And that's just something that you can read off directly from the Lagrangian. But I'm sure there's other ways to see it that sounds interesting.
Okay, thank you.
Other questions? All right, so so because of the attractor mechanism, it turns out that the cone of BPS black holes contains the moduli space itself, because because there's this correspondence between charges and moduli vivs. And so expressed in a certain set of flat coordinates, we find that the cone of black holes contains this set of values here, which is a lot of symbols, but this is really just something called the extended Kähler cone of the Calabi-Yau. Okay, so these coordinates sweep out the dual of the effective cone, which is the cone of holomorphic force cycles. So as long as we can find the effective cone or its dual, then we've found this region. And so the upshot is that we need to compute the moduli space of the Calabi-Yau. And the moduli space is the extended Kähler cone. So let's dive into that a little bit. So how do we get the extended Kähler cone from toric geometry? Well, here's a way you might think that you can get the extended Kähler cone. So let's consider a Calabi-Yau threefold X, which is given as a hypersurface in a toric variety, whose toric fan is a fine regular star triangulation of a four-dimensional reflexive polytope, delta. And again, the goal is to find the extended Kähler cone of X. So one reasonable approach would be to find all FRSTs of the polytope delta and stick their fans together. And what you would find is a picture that looks like this. So this is a cross-section of this FRST extended Kähler cone for a polytope with H11 equals 491. And so what we're really seeing here is a cross-section of each one of these little polygons is a cross-section of a Kähler cone of a particular Calabi-Yau given as an FRST of this polytope with H11 equals 491. Okay, but it turns out that this FRST extended Kähler cone is not actually the entire extended Kähler cone. Okay, so there can be chambers of the extended Kähler cone which are not related to the original Calabi-Yau by changes in FRST, and we call these non-toric phases. Okay, so in this picture, I'm representing these non-toric phases by this big red blob. And the point is that in general, there can be lots of non-toric phases. And in fact, it seems like at larger H11, there are even more non-toric phases than toric phases. And so if we want to get a handle on the entire extended Kähler cone, we're going to need to understand how to compute these non-toric phases. So in other words, we need to find all of moduli space. Okay, so now we come to the part where we get to start reconstructing Kähler moduli space using Gopa-Marvaka invariance. Okay, so maybe I should say, sort of to frame the overall picture, these GV invariants are coming into two parts of the story. The first part that they come into is motivated by the weak gravity conjecture, which I was explaining earlier, that they can give us a signal of where in the charge lattice we have non-vanishing BPS states. But the second place that they come into this story is that we're going to be using the GV invariants themselves to reconstruct the extended Kähler cone. And so that's what I'll explain how to do now. Okay, so I alluded to this just now, but given only the Gopa-Kumarvafa invariants of a Calabi-Yau, we can actually reconstruct the entire extended Kähler cone. And the rough idea is that the GV invariants tell us which
need only the genus 0? Only the genus 0, guys?
Only the genus 0. That isn't we don't have like an airtight proof that that's sufficient, but it seems to be that as you go up in genus, the GV invariants sort of the cone generated by the non-vanishing GV invariants gets smaller and smaller, and so of genus, and so it seems to be that all you need is the genus 0, but I'm not claiming that that's an airtight proof. Okay, so the rough idea is that these GV invariants can tell us which curves can be shrunk without inducing an infinite number of massless states. So first, let's describe how this works, and then we'll go back to our H11 equals to 2 example from earlier and see how it works in application. Okay, so to understand how to reconstruct moduli spaces, we need to understand the physics that can happen along facets of Kähler cones. So as a reminder, and maybe I didn't explicitly say this, but the extended Kähler cone is the union of all Kähler cones of all birationally equivalent geometric phases of a particular Calabi-Yau. So if I have some Calabi-Yau X, I find all of the Calabi-Yaus that are birationally equivalent to X, and I stick them together, and that's the extended Kähler cone of X. And so to compute it, we need to understand the possible physics along facets of a single Kähler cone. And there's really 4 possibilities. The first is that we have a flop transition. So in a flop transition, a finite number of states becomes massless along a facet of the Kähler cone. There's another possibility, which I won't go into too much in this talk, but there's a possibility that there's an SU2 enhancement in which a finite number of states also becomes massless. And in fact, this is really just like a flop, but where you've tuned the complex structure moduli to some particular locus. Then we can have a strong coupling limit in which an infinite number of states becomes massless. And finally, we can have an infinite distance limit where, again, an infinite number of states become massless. So these are the possibilities. And again, for this talk, we're not going to worry so much about these SU2 enhancements, but feel free to ask me about it afterwards. But there's nothing too complicated going on here. It's just an added subtlety that I don't want to deal with in order to get the point across. Okay, so let's look at our example from earlier and see how we can see these different physics ideas coming out. So the first is I told you that there can be facets of Kähler cones where a finite number of states becomes massless, and that would be corresponding to shrinking a curve like this one, where we have a single non-zero GV invariant, and then the rest are 0. And what you can see, and we'll see this in a second, is that in the limit where you shrink this curve, you can actually analytically continue the prepotential without any sort of trouble. And so that's how we know that this corresponds to a flop transition. And then the other kind of physics that can happen is if we shrunk a curve like this one, where in principle we have an infinite number of non-zero GV invariants. And so if we shrink a curve like this one, then an infinite number of states becomes massless. And that's either corresponding to a strong coupling limit or an infinite distance limit. And I forget which of the two shrinking this particular curve corresponds to. Okay, so the goal is to, from these patterns in GV invariance, identify flops. Once we've identified all the flops, then we can reconstruct the extended Kähler cone. Okay, so before we dive into that, I have to unfortunately give you a few definitions. The first is something I'll call a nilpotent curve, which is a ray in the BPS cone with finitely many non-zero GV invariants. Okay, so that would be a curve like this one. The second is a potent curve, which is a ray with infinitely many non-zero GV invariants. So each ray inside this blue curve, or sorry, inside this blue cone is what I would call a potent curve. And finally,
shouldn't it be called a wedge? Shouldn't it be called a wedge, not a curve?
Sorry, each
So any line inside that will be what you will call a curve, right? Okay.
Yeah, I guess I'm being a little sloppy with what I call curve and what I call ray. By potent curve, I really mean a curve inside a ray with infinitely many non-zero GV invariants.
Okay, okay.
So for example, like 1,0 here, I would call a potent curve because it's a curve inside a ray with an infinite number of non-zero GV invariants.
Okay.
Yeah. And then lastly, I'll call some nilpotent curves can be outside of the closure of the cone generated by potent curves. And so that's what I'll call a NOP curve. NOP stands for nilpotent outside potent. But really, we can just think of these as flop curves. All right, so this red ray is both containing a nilpotent curve and a NOP curve. Okay, so how do we now reconstruct the extended Kähler cone? So as a computational tool, we'll compactify our 5D theory on a circle to obtain a compactification of type 2A string theory. And so the pre-potential now takes this form. So we have some polynomial piece, which depends on the triple intersection numbers of the Calabi-Yau, as well as the Kähler parameters. And then we have this infinite series of instanton corrections, which depend on the genus 0 Gopkumar-Vafa invariance, as well as on the curve classes and the Kähler parameters as well. All right, so now let's take some curve C0 to be one of these NOP curves. So this is a nilpotent curve that's outside of the cone of potent rays. And let's vary the Kähler parameters such that the volume of this curve C0 formally becomes negative. And the upshot is that by doing this, what happens is that we go from the Kähler cone of our original Calabi-Yau to the Kähler cone of some new Calabi-Yau x prime, which is birationally equivalent to x. Okay, so now we can see in the next slide how we actually compute the geometric data of x prime, so the triple intersection numbers and second Chern class. So let's now start with the pre-potential that I showed you earlier. So again, the pre-potential has this polynomial piece, which depends on the triple intersection numbers and the Kähler parameters. And then this, in the last two terms in this expression are the infinite sum of instanton corrections that I showed you before, except that now all I've done is I've singled out the one instanton correction that corresponds to our NOP curve C0. Okay, so this entire thing is the exact same sum as we had before, except we've singled out this one correction that corresponds to the NOP curve. Now, as promised, let's assume that the volume of this NOP curve is formally negative, and write this whole expression in terms of some new curve C prime, which is just the opposite of C0. So if I just do that, I plug in C0 is minus C0 prime, I get the exact same expression as I had before, except now all that happens is I flip the sign of this exponent. Okay, so that's all that happens. And now we can use this polylogarithm identity, which says that the trilogarithm of e to the minus x is the same as the trilogarithm of e to the plus x up to these polynomial corrections. So if we plug in this identity, then what we find is that we end up with a prepotential that looks a lot like the one we started with, except that this polynomial piece has changed, right? Because of this polynomial piece in the polylogarithm identity. And now we've replaced our trilogarithm of e to the minus blah with trilogarithm of e to the plus blah, okay? And so what we've ended up with is the prepotential for what looks like a new Calabi-Yau x prime with some new triple intersection numbers that have been shifted because of this identity. All right, so let's take a step back and ask what we've learned so far, because I've thrown a lot at you. What we've learned is that an isolated generator of the Mori cone with a finite number of non-vanishing GV invariants can actually be flopped in order to obtain a new Calabi-Yau. And so by performing all available flops to uncover all Calabi-Yaus that are birationally equivalent to the original one, we can determine the entire extended Kähler cone. And so now let's apply this machinery from start to finish in a concrete example. So let's go back to our example with h11 equals 2. This is a Calabi-Yau with h11 equals 2. We have here in purple the Mori cone of x. And again, I've just labeled all the GV invariants that we can compute inside this cone. All right, so for visual clarity, I don't want to keep writing the GV invariants every single time. So instead, I'll just put a dot at every site with a non-vanishing GV invariant. So if we just toggle between these two slides, we see that everywhere there's a non-zero GV invariant, I'm putting a dot, and everywhere there's a zero GV invariant, I'm not putting anything. Okay. So again, we remember that it's this special curve in red that we said is a curve that can be flopped, which means that we can take C0 to minus C0 without inducing any infinities in the prepotential. And we're supposed to, when we do that, get a new Calabi-Yau x prime, which is birationally equivalent to x. So let's do that. Let's take this curve C0 and flop it to minus C0. And what happens when we do that is that we end up with a new Mori cone, which is this entire pink cone here, which is the Mori cone of our new Calabi-Yau x prime. And a fun fact about this particular example is that this new Calabi-Yau x prime that we find in this example is not in any of the known databases of Calabi-Yaus. So what we've really uncovered here is a genuinely new Calabi-Yau. All right, so how do we get the extended Kähler cone from this picture? So this is just the same picture I had before. In blue, we have the Mori cone of...
Just quick question, how did that happen? It's non-toric?
Yeah, so the new Calabi-Yau that we have here is not is not a Calabi-Yau that can be described as a hypersurface in a toric variety or as a complete intersection Calabi-Yau.
Okay.
Okay, so we have this picture where we have the first quadrant being the Mori cone of x. We have this pink cone being the Mori cone of x prime.
Sorry, and then one more question. Under flops, H11 doesn't change, right? I mean, it's the same.
That's right. Yeah.
So the Betty numbers would be the same for or the Dolbu, whatever. But the triple intersection. So you're looking at more details of from the database. You're looking at the triple intersection numbers as well, right?
Exactly.
Okay.
Okay, so now if we take the straightforward cone duals of all these cones, we're going to end up with some cones on the Kähler side, and let's see what we find. So if we take the cone dual of this blue region, we end up with the Kähler cone of x, which the cone dual of the first quadrant is still just the first quadrant, so the Kähler cone of x is just the first quadrant. If we take the cone dual of this entire pink region, we end up with something narrower, which is this pink region over here. This is the Kähler cone of x prime, our new Calabi-Yau. And so this entire cone, the union of the blue and the pink regions, that's the extended Kähler cone. So that's how this works. And finally, now we can go back in this example to checking the weak gravity conjecture. So let's see how that happens. So we have our extended Kähler cone here, and we can apply this dual coordinate map that basically tells you by the attractor mechanism where all the spherically symmetric black holes are. And what we end up with is this yellow cone here, T. And so what we see in this example is that every site in the purple region hosts a BPS state. And our black hole region is contained in the purple region. And so the lattice weak gravity conjecture is satisfied in this one example. So that's how the check of the weak gravity conjecture goes. But now we can use this machinery to check the weak gravity conjecture in a large ensemble. So we now have an algorithm in order to verify the weak gravity conjecture. How does it go? Well, first we compute the Gopu-Kumar-Vafa invariants. Then, using those, we determine the extended Kähler cone by going through all possible flops. Then we apply the dual coordinate map to the extended Kähler cone to obtain this black hole region. And finally, we ask, is every site in that region populated by a non-vanishing GD invariant? And so we performed exactly these steps in over 2,000 Calabi-Yaos constructed as hypersurfaces and toric varieties, and we found that the lattice weak gravity conjecture was always satisfied. Okay, so that's kind of the upshot of our results on the weak gravity conjecture. But I also wanted to tell you about what we found about just uncovering these non-toric phases. So these are our results on the non-toric phases that we uncovered. So you can see that at H11 equals 2, there's just a few. Okay, so let me explain these what these pictures mean. So the x-axis here means basically nothing. This is just an arbitrary ordering from the Kreuzer-Skarka database. It actually happens to be ordered by H21. And in blue is the number of toric phases for each polytope. So in blue is the number of FRSTs of a particular polytope that we find. And in orange is the number of non-toric phases. So these are Calabi-Yaos that result from flops of the original toric Calabi-Yao, but can't be described as a hypersurface in that toric variety. Okay, so what we see is that as we go up in H11, of course, the number of FRSTs tends to grow, but also the number of non-toric phases tends to grow. And already by H11 equals 4, non-toric phases seem to start to dominate over toric phases. And we actually have a paper coming out next week, which is determining which of these Calabi-Yaos are actually topologically inequivalent from each other. So keep an eye out for that. Okay, and as a
what do you mean by topologically inequivalent?
Yeah, so for any two Calabi-Yaos in this data set, you could ask, so by Wall's theorem, if two Calabi-Yaos have the same triple intersection numbers and second Chern class, then they're homotopy equivalent. And so you could ask, I have this set of Calabi-Yaos here, and but are they all really distinct Calabi-Yaos, or are some of them actually equivalent to each other? And so what you can do is try to find basis transformations that take you from one Calabi-Yao to the other. And in these data sets, we can actually prove which Calabi-Yaos are inequivalent.
Okay, thank you. And one more thing, did you put in a restriction that the attractor fixed points must be at large volume by any chance? Did you do that?
Yeah, large volume. Well, so in our checks of the weak gravity conjecture, we're doing M theory, so we're really restricted to the overall volume being 1.
Mm-hmm.
Do you have something in mind?
No, it's just that so you should, but in M theory, there's also the other non-geometric phases get crunched. So yeah, I think you'll be fine. Yeah, sorry.
Okay,
You'll
cool.
be fine. I don't want to ask my question now.
Okay, it'll be fun to talk about it later though. So as a last sort of aside, it's interesting to see how the weak gravity conjecture can actually inform geometry. So I think this is one of the coolest things in physics is when we not only use math to teach us about physics, but when we can actually start to use physics to teach us about math. And so there's something that here that the weak gravity conjecture actually teaches us about geometry, if true. So what we've seen is that the cone of BPS black holes is related to the cone of effective divisors, E. And we've computed effective cone duals in large ensembles of geometries and verified that all those sites are populated with non-zero GV invariants, thus satisfying the weak gravity conjecture. Okay, so we did that explicit check, but what we can ask is whether we can turn the logic around and actually use the weak gravity conjecture to constrain effective cones. So here's an example of how this might work. Suppose we have some approximation to the true effective cone, such that our approximation was an inner bound of the true effective cone. Then if we plot its dual, it might look something like this green region. And here I'm just making up some example to show how this would work. And so in this example, what we see is that there are empty sites in the dual of our approximation to the effective cone. And so if we had an example like this, we would say that the weak gravity conjecture actually predicts that the effective cone that was our approximation is too small. And so that the weak gravity conjecture in this example predicts that the Calabi-Yau should actually have more effective divisors than we thought. And this is something that we can explicitly check, and we have, and it always works out that when you have a situation like this, you can actually go into the Calabi-Yau and find more effective divisors such that the weak gravity conjecture ends up being satisfied. And so in this example, the resolution might be that the dual of the true effective cone is actually smaller, so that every site inside this effective cone is populated. And so your true effective cone was actually bigger. All right, so let me just conclude, and then I'll share some sort of like food for thought about this project. So what did we do? We used genus 0 Gopakumar-Vafa invariants to reconstruct the Kähler moduli spaces of Calabi-Yau threefolds. And equipped with the full Kähler moduli space and collections of BPS states, we verified the weak gravity conjecture in a whole ensemble of examples. And as promised, I'll just leave some food for thought. So all of the examples that we checked appear to satisfy the weak gravity conjecture already with genus 0 GV invariants. So, you know, is there some deep reason for that, or is it just coincidence? Like I was saying, that the cones tend to get smaller and smaller, so you already see everything with the genus 0 GV invariants. Also, as I've stated throughout, all the examples that we checked actually satisfy this stronger version of the weak gravity conjecture, the lattice weak gravity conjecture, which we know is not in general true. So why is the lattice weak gravity conjecture being satisfied in this ensemble? Is this just a lamppost effect that we only check the smallest H11 examples, or does it have something to do with toric hypersurface Calabi-Yaus? Why don't we see any examples that violates lattice? And this comes back to the question before about non-spherically symmetric black holes. So what we often see is that there are infinite towers outside of the cone of spherically symmetric black holes that we compute. It might be that the infinite towers outside of this region still play some role for the weak gravity conjecture, and it could have to do with non-spherically symmetric BPS black holes. So it would be really interesting to see if that were true in any sense. And finally, we don't have a lot to say about what happens when the attractor flow runs into these strong coupling CFT boundaries, but it would be good to know that as well. And so with that, I will say thank you.
thanks for this nice, very, very nice talk. So we should have more questions now. So
Just to understand, your black holes only carry electric charge. By that, I mean, in the type 2A language, they just carry D0 and D2 charges, right?
That's right. That's right.
Right. Okay. So because the multi-centered black holes are usually electric magnetic bound states and stuff like that.
Right. Right.
So there is no wall crossing or anything like that for Gopakumarvaka because they're just D2, D0 counting. So, I mean, earlier I was asking you about, so I don't know if there are two-centered BPS solutions which are pure electric.
Right.
Do you know the
right.
answer to that? I mean, I would say no, but I don't know the answer.
Yeah, definitely all the examples I've seen of multi-centered black holes are dionic black holes. But yeah, I'm not sure in general.
Yeah. So yeah, the other question was about large volume, etc. Again, it's like I have been always thinking about dionic black holes. So I'm actually busy withdrawing my questions because the problem there is that if you think of what would see the large volume is something like a 6-brane wrapping the whole Calabi-Yau, but that's a magnetically charged object, and that's not something you are studying. And
Right.
so what you have done is really so the volume is for you some fixed number, you can always normalize it to be 1. Otherwise, you could go into phases where the Calabi-Yau is shrinking, etc. But I suspect that the D2, D0 black holes would not see that. So.
Well, it definitely can be the case that you can run into boundaries where weird things happen, like an infinite number of states becomes light. It's just that there we would say that that's the exterior boundary of moduli space rather than a finite distance transition.
Yeah, but how do we understand it from D2, D0 brane setting? I mean, that I don't have a feel for.
Yeah, I don't think I have a great answer to that. I would need to think about it a bit more, but that's interesting.
Okay, thank you.
okay, and actually, let me ask some very general question, maybe not exactly related to this talk. So what it will, so here you're checking the weak gravity conjecture example, and clearly it was, we learned something about mathematics from here, but interesting, but question is what it will take to prove it, prove weak gravity conjecture. I mean, instead of checking it, I mean, what needs to be done to prove it?
Oof. Yeah. I mean, in general, I think it depends which version of the weak gravity conjecture you set out to prove, right? I mean, there's some, there's arguments, for example, from like higher derivative corrections that black holes by themselves are enough to satisfy them. And so if you're happy with like a weak enough version of the weak gravity conjecture, then maybe in some settings it's already proven. But it's tricky. I don't think that the answer to your question is very well defined because we haven't like fully defined the question itself yet. So I think we need to understand better which version of the weak gravity conjecture we really expect to be true and why before we go about proving it. And I think that I guess I would say that we're still in the stage of formulating the question, right? Which is why we're doing all these explicit checks of the weak gravity conjecture, because we want to see what's actually true in string theory.
But let me phrase the question in another way, maybe. So suppose you said that you know some examples where this lattice weak gravity conjecture is not true. Are those examples inconsistent or not? I mean,
No. They're totally fine examples. These are like compactifications of heterotic string theory. There's nothing weird about them. What's weird is that in our setting, we don't find examples that violate lattice.
They're consistent in the sense that the extremal black holes can still decay there, even though the lattice weak gravity. Yeah.
Yes. Yeah.
So
So those examples satisfy a sublattice weak gravity conjecture. So in those cases, instead of the full lattice being populated, it's a sublattice.
So the general statement is that that extremal black hole should be able to decay, and there should exist some decay mechanism. But what it implies for the spectrum is not often clear. So this is the main.
Absolutely, and I think that part of answering that question will be maybe providing some better motivation for that bottom-up argument of black holes should be able to decay, because right now, like, there's no very clear reason why, from like a quantum gravity perspective, that should be true, you know? So I think once we have a better handle on like the real like mechanisms and structures at work, we'll be better positioned to actually go about proving it.
Okay, thanks. So thanks a lot again for this. If there are no more questions.
No, I have one more question.
Okay,
I mean,
sorry.
outside the T, what do we make sense of that? I mean, you've checked inside the region which you call T or tau, right? Outside that region, what, I mean, how can we make sense of points in that? Because that's inside the cone.
Yeah. So that's that was one of my questions on this.
Yeah. Which I want I want to ask you to tell us more. Sorry.
Right. Yeah, I don't know. It could be, you know, like black holes with angular momentum or something, that there's a weak gravity conjecture there that these states, you know, need to satisfy.
Okay.
Yeah,
there is some version of attractor mechanism for rotating black holes. I think my colleague Prashanta Tripathi and Sandeep Trivedi had looked at it many years ago. So there is some story there. I forgot it.
There absolutely is. Yeah, I just don't have a very good handle yet on like what the weak gravity conjecture should imply for those black holes, and but I think it's a really interesting question, and it would be great to answer it.
Thank you.
Okay, so
beautiful slides. I want to say and allowed some transitions. Really wonderful. Thank you for taking it.
Yeah, indeed. Yeah, it was quite a pleasure. Okay, so then we can officially close the recording.